Okay, so we have a satellite at an altitude h, meaning that the total distance between the center of the planet and the satellite is the radius plus the altitude, r plus h. What is the force at that height? So the force due to gravity equals g, the mass of the planet, the mass of the satellite over the distance squared. As the height increases, the force of gravity becomes less. What is the acceleration due to gravity g, or else the field strength? Well, the same, as we know that g is the force over mass, we should say that it's g, the mass of the planet, r plus h squared. Okay, so if we want to find the acceleration due to gravity on that height, it will be the universal constant times the mass of the planet over the total distance squared. So we see that wherever the satellites, in order for the satellites to turn, there has to be a force, so there has to be an acceleration due to gravity. And not only for the satellites, but for everything that is in the satellites, the people. So the people in the space station, for example, we have a state of weightlessness. They do have acceleration, otherwise they wouldn't be able to move around the Earth, right? But just because the space station and the people there, they feel the same acceleration, the acceleration due to gravity g, that makes them rotate, the normal force, the force from the floor is zero, not the force of gravity. The normal force is zero. There's no normal force because the astronauts and the space station do the same motion. They have exactly the same acceleration. They do the same motion, so there are no forces in between them. So we have a state of weightlessness. We do have weight there. The space station, the astronauts, they have weights. Okay, but the weight is used to rotate them, to make them orbit around the Earth. That is why we have a state of weightlessness.